All right, thank you. And thanks for all being here at 9 in the morning. So I'm going to be talking about planning with multiple biases, joint work with John and Sigal, who's here. And this is going to be a kind of a modeling problem in behavioral economics that we're going to look at. Specifically, we're going to say, what happens if we look at agents that exhibit multiple behavioral biases simultaneously? So the first bias that we're going to look at is sunk cost bias, which many of you may be familiar with. And I'm going to give you an example from a paper by Dick Thaler, which there's a family that pays for basketball tickets and drives 60 miles through a snowstorm to go see a game. But they note that if these tickets had been given to them for free, they would have just stayed home and not gone. So this is not the rational thing to do in this situation, right? This cost has already been incurred. You shouldn't be taking it into account when making future decisions. But this is something that we do a lot. And this is actually commonly known as throwing good money after bad, which is you've already sunk some cost into something and now you spend even more effort trying to prevent yourself from, in your mind, losing the cost that you've already sunk. Maybe the most classic example of this is with the development of the Concorde airplane. This was a supersonic jet that was used from the 1970s to the early 2000s. And it was continued to be used despite the fact that it was very clear that it was no longer an economically viable means of transportation. But people didn't want to admit that. And this became such a classic example that this is sunk cost bias is also commonly known as the Concorde fallacy. So the other bias that we're going to be looking at is present bias. And this has received a lot of attention over the last half century in the literature. It leads to things like procrastination and task abandonment. The example I like to give is that people's New Year's resolution is commonly to get a gym membership, and they think they're going to go to the gym all the time, but somehow when the time actually comes, people just end up staying on their couches instead because the cost of getting up and going to the gym seems to be much higher than what they had previously estimated. And so you could ask, how are these related, and why am I even talking about them together? And intuitively, here's why. Present bias makes you want to abandon a task. It makes you not want to keep going anymore. The cost seems too high, you just want to stay home. Sunk cost bias, on the other hand, has the opposite effect. It pushes you forward. It makes you want to keep going despite the fact that things look expensive. And so the key question that we're going to focus on here is, how are these things interacting? You have two forces that seem to be pushing you in opposite directions. What happens when they come together? Are they going to make each other worse? Will they cancel each other out? Will they exhibit complex interactions? And so that's going to be the focus of this talk. So to talk about this, I need to give you a little bit more math. And so the standard model for procrastination and present bias is that the cost of the immediate action that you're going to take gets multiplied out by some factor b larger than 1. And this is consistent with, this is from quasi-hyperbolic discounting. And for those of you who are familiar with it, I'm going to assume that there's no discount factor, so future costs will actually remain unchanged. And so for sunk cost bias, the intuition here is that the more effort you've invested in something, the less likely you want to give it up. And so the way that we model this is that the cost of giving up a task increases linearly with the amount of effort that you've put in. And we'll actually see that in our model this is equivalent to assuming that your perception of the reward increases linearly with cost incurred. And so this is consistent with models from behavioral economics like mental accounting and realization utility. Okay, and so I'm going to present to you an example to get a feel for the way that these calculations work. And so for this example and for the remainder of the talk, I'm just going to say b and lambda are 2 and 1/2 respectively to keep things simple. And so the example I want to give is as follows. You want to go take a yoga class, and you believe that the reward for doing so will be 19. And I'm working in arbitrary units here, but let's not worry about that too much right now. The cost of actually buying this membership is 1. So if you go into this yoga studio, you buy your membership, that costs you 1. And then on the day of the class, you have to pay to attend this class. And the amount of effort required to get up off your couch and get yourself to the yoga studio is 10. Okay, so right away we look at this and we say, well, the total cost that you would incur is 13, the reward is 19, so this seems like a good thing to be doing, so obviously the optimal thing to do is just sign up and take this class. But let's ask what happens when you have a biased agent instead of an optimal one. So on the day that you have to buy this membership, the perceived cost of doing so is, remember, B times the immediate cost that you're going to incur, plus the total remaining cost. So B times 1 plus 12 is 14. 14 smaller than 19, so you see, great. This looks like this membership will be worth it. I'm going to buy it. And in doing so, you've sunk some cost in. Right? You've invested a cost of 1. And so your perception of the reward increases slightly from 19 to 19.5. However, on the day that it comes that you actually have to go to this class, you look at this and you say, now I need to invest an effort of 12. But because you're biased, this gets multiplied up by a factor of B. And it turns out that the perceived cost of doing so is going to be 24, which is much larger than your perception of the reward. So it no longer looks like this is worth it, and at this point you'll actually abandon this task and say, no, I know I've invested an effort of 1, but I'd rather just stay home on my couch and not go. And so for those of you who are familiar with procrastination, which I would assume is most of us, this is not that surprising, that you change your mind halfway through something because you realize it seems more expensive than you previously thought. But what I'm going to do is actually ask a slightly different version of this question now. So let's call this the basic membership, where you pay 1 up front and then 2 to actually go for the class. What if I offered you a different membership instead, this deluxe membership, where instead you pay 4 up front, but the class itself is free? Okay, now you could argue, well, this is kind of silly because it's a more expensive membership. Why would anyone do this? Right? But supposing it was offered to you, let's reason about what would actually happen. On day 1, you have to get this membership, and again you do the same computation. B times the cost that you're about to incur, plus the remaining cost. In this case it's going to be 18, which is still smaller than your reward of 19, so you say, fine, it's more expensive, but I'd still be willing to buy this membership. And now you've sunk in a cost of 4. So your perception of the cost, or perception of the reward, is actually increased from 19 to 21. Right? And now the punchline is, on the day that you actually have to go to the class, your perceived cost is B times 10, which is 20. Your perceived reward is 21. And so somehow this is actually high enough to motivate you to get up and go. So it's some combination of the reward on its own, plus knowledge of the cost that you've sunk so far, that has made this perceived reward large enough that you'd be willing to take it. Okay, so in this example, I offered you a strictly worse membership, but somehow it led to a strictly better outcome. And so this is kind of the paradox that is a lot of these behavioral biases. And sure, this is an interesting story, but I want to be able to talk about these things more generally. And in order to do that, I'm going to turn to a graph theoretic model developed by John and Sigal a few years ago. And it's quite straightforward. You have a directed acyclic graph where each edge represents an action and has an associated cost. And your goal is you start at some node S, you want to reach a target T where there is some reward waiting for you. And this actually maps exactly to this story that I just gave you, where the top branch corresponds to your basic membership and the bottom branch is your deluxe membership. Okay? And now that I've introduced the formalism of this graph, I can be a little bit more clear about what I mean when I say the perceived cost and the perceived reward. So when I say the perceived cost, what I mean is as follows. If you are at some node U and you are considering going to some node V, some successor node, the perceived cost is simply B times the cost of the edge between U and V, plus the cost of the remaining path from V to T. And I'm being a little vague when I say the cost of the remaining path, because there could be multiple ways of getting from V to T. Which one are you going to use in your evaluation? And so this path is going to be the one that you believe that you are actually going to take. And how you form this belief is actually very important, and we're going to come back to this in a second. Because how you form this belief greatly affects the way that you plan. But just to finish up here, we can look at the perceived reward. And this is pretty straightforward. It's just the perceived reward after you've taken some path from S to U is simply the original reward plus lambda times the cost that you've incurred so far. Okay? And then the way that an agent plans is it just says, I'm going to choose the successor node V that minimizes perceived cost, and I'll give up on this task if there is no such node that has perceived cost larger or smaller than the perceived reward. Okay? And so now what I need to do is fill out what I mean by believed path. And so to do that, we have to ask the question, how do agents actually form beliefs about their future actions? And this actually hinges on a very important question, is, are people aware of their bias? And there's a couple answers to this. There's evidence to say, no, we're not aware of our bias. We make plans and then don't keep them. We change our minds all the time. And so agents that do this are what we call naive. To be naive is to believe that you will act optimally in the future. You exhibit bias now, but somehow you think, I don't feel like going to work today, but actually tomorrow will be better, and I'll end up doing it then. So maybe this is familiar, again, to a lot of us. But on the flip side, you could also think about agents that are sophisticated. Agents that actually take into account their bias and plan as if they'll be biased in the future. And let me be clear, this is not the same thing as saying agents that are aware of their bias and therefore get rid of it entirely. This is a different thing. What this is saying is the type of agent that says, I know I don't want to work today, but I also know my future self tomorrow won't get any work done. It's not a question of correcting for your bias so much as being rational or being accurate about what your future self is going to do. Okay? And so it's unclear whether humans are actually naive or sophisticated or some mix of the two. And so what we're going to do is actually have different types of agents corresponding to various degrees of sophistication and actually draw comparisons between them to see what they're going to do. The way that we do this is on top of their actual bias parameters B and lambda, we're going to have these believed bias parameters B prime and lambda prime, which is what the agent actually thinks that they are. And this will actually be used for this is how the agents will form their beliefs about their future paths. So here's a few types of agents we consider. There's the doubly sophisticated agent, which is just sophisticated about both of its biases. It knows how present biased it is, it knows its degree of sunk cost bias, and it can use these to plan accurately in the future. Maybe the opposite of this type of agent is the doubly naive agent, who is completely unaware of their biases. The doubly naive agent believes it will act optimally in the future. So B prime and lambda prime as 1 and 0, those are exactly the parameters that an optimal agent would have. And somewhere in between, we could have this singly sophisticated agent, which knows about its present bias, but is totally unaware of its sunk cost bias. Okay? And we'll see what types of comparisons we can draw between these, and also we'll compare to a slightly different type of agent, which is a sophisticated agent with no sunk cost bias at all. And this is a type of agent that we looked at in previous work. And you can get all sorts of nice performance guarantees and characterizations of this agent. And so the question is, how do these three types of agents that I've introduced compare to this one? And the final thing that we'll compare to is simply the optimal agent that does the right thing all the time, has no bias, takes the shortest path through the graph. Okay, so let's go back to our yoga example and ask, what do various types of agents actually do in this example? So the doubly sophisticated agent does something pretty interesting. It realizes that if it were to go from S to U, it would give up this task entirely at U and never complete it. And as a result, it says, this basic membership isn't for me. I know if I buy the basic membership, I'm not going to end up going to class. What I need to do instead is buy this more expensive deluxe membership, and because it's more expensive, it'll push me on to actually reach my goal. And so it does that, it buys the deluxe membership, reaches the goal, and things are great. The doubly naive agent, on the other hand, as you might expect, thinks, well, there's two memberships, the basic membership seems cheaper, let me do that. And so it does, it buys the basic membership, and then it gets halfway through and realizes, actually I'm feeling too lazy, and I didn't really invest that much in it, so I'm okay giving up on this altogether and not going to the class. And somewhere in between is this singly sophisticated agent, which says, neither of these options look great to me because I know that I'm going to be biased in the future and won't want to get off the couch. So actually I'm just going to stay home and not even buy a membership at all. So interestingly in this example, all three agents are exhibiting different behaviors. And so in the full paper, we have all sorts of performance guarantees and worst case characterizations of these things. I don't really want to get into that. Instead, what I want to talk about are the qualitative insights that we can get from these various different types of agents. With a doubly sophisticated agent, what we found interesting here is you actually get the same performance guarantee as an agent that is sophisticated with no sunk cost bias, which is you're within an additive factor of optimal. And you can actually show that these results are robust, that as long as you model sunk cost bias in a way that is non-decreasing, where the perceived reward is non-decreasing in cost incurred, these results hold. Which is great, except for the fact that the actual path computation problem for doubly sophisticated agents is NP-hard. And so maybe this is some sort of evidence that people don't actually behave this way. And the real issue is that the choices of future paths are themselves path dependent. It depends how you got to V to know what you're going to do going forward from V. Okay, and this is done, we can show this through a reduction from subset sum, which I don't really have time to get into. But you can see the paper for more details there. What we found really surprising about this singly sophisticated agent is that they can actually do really, really bad things. They can be exponentially bad, they can abandon tasks, and that's not something that agents, if you're sophisticated and you don't have sunk cost bias, that's not something you do. And so our intuition that, okay, sunk cost bias should only make things better because it makes you more likely to get to the target, that's just simply not true. It can actually have these complex interactions that bring in effects that you wouldn't see without. And so this kind of tells us that we have to be careful in our modeling when we look at agents, and we have to be aware of all the biases that they have, really. And finally, doubly naive agents can also be exponentially bad, which is less surprising to us given that, in general, naive agents can do some pretty terrible things. But the interesting thing here is that the biases are actually separable. You can show that the present bias determines which path the agents will attempt to take, and the sunk cost bias determines how far along that path they'll get. And so maybe this is an instance where you can actually look at the biases in isolation because there's a more simpler, a more tractable interaction between the two. Okay, so just to sum up, multiple biases can interact in really challenging ways. They can make computation hard. They can kind of destroy all the guarantees that you thought you had. And they can produce these pathological non-monotонicities that go against your intuition. And so all these points to the fact that we just need to be careful when we look at agents, and we need to be careful about modeling all their biases in order to really say reasonable things about them. In the future, you could ask a lot of questions here. One thing that we're actually not even sure about is, if we're a doubly sophisticated agent, if you tell me what path they're going to take, can I verify that that's true? That's not entirely obvious. You could ask things from a design perspective of how should I design tasks to take into account that I might have agents with these biases and maybe a heterogeneous mix of biases. And finally, you could look at how a broad range of biases interact with each other. One thing that we've thought might be interesting is looking at phenomena in risk aversion and prospect theory in kind of probabilistic settings. So all these could be really interesting to look at in the future. And thank you.